Hello people, hope you're all safe wherever you are. I am Sai Ayachit and this is my team. We are final year computer science students at the National Institute of Engineering, Mysore, and we were a part of the IBM Global Remote Mentorship Program 2020. Today, we are here to demonstrate our work, competitive analysis of the top gradient boosting machine learning algorithms, which was carried out as a part of the GRM program. Before we start off, we would like to acknowledge the constant support and efforts extended by our project mentor, Mr. Sangeet Kiryadat, who is a senior developer at Systems Development Lab, IBM, and our faculty mentor, Mr. Abhinandan SP, who is a professor at the Department of Computer Science and Engineering, NIE. We would also like to thank IBM India for providing us with this amazing opportunity through the GRM program. We live in the 21st century, where machine learning has become an integral part of many solutions, owing to the rapid increase in computing power and data-driven approaches to tackle many real-world problems. With the advent of competitive machine learning, we started witnessing a surge in highly accurate and fast machine learning algorithms. According to a Kaggle survey in 2019, boosting algorithms are among the top 3 preferred methods used by data scientists for competitive machine learning tasks. Gradient boosted decision trees, or GBDT, is one of the techniques that utilize gradient boosting to its advantage and has seen a wide range of commercial and academic applications. Gradient boosting is similar to AdaBoost in a way that they both use an ensemble of decision trees to predict a target label. However, unlike AdaBoost, the gradient boosted trees have a depth larger than 1. So what exactly does boosting mean? In simple words, it is combining a learning algorithm in series to achieve a strong learner from many sequentially connected weak learners. In the case of the GBDT algorithm, the weak learners are decision trees, where each tree attempts to minimize the errors of the previous trees. Unlike bagging, boosting does not involve bootstrap sampling. Every time a new tree is added, it fits on a modified version of the initial dataset. Since trees are added sequentially, boosting algorithms learn slowly. In statistical learning, models that learn slowly perform better. GBDTs are considered a black box model, and our research makes an attempt to help improve its explainability across several use cases. And to do that, we perform an exhaustive 360-degree comparative analysis of 4 state-of-the-art gradient boosting algorithms, XGBoost, CatBoost, LightGBM, and IBM's novel SnapBoost, by training and testing them on diverse datasets, which included numeric, categorical, image, and temporal datasets, while leveraging IBM's PowerAI AC922 CPU. These algorithms were validated for being robust against overfitting, ability to handle categorical variables, and multimodal data, while leaving a small memory footprint. The analysis was performed using 2 approaches. The first one was using the baseline algorithms, and the other one was by performing systematic hyperparameter optimization using the HyperOpt framework. Although the HPO process is resource intensive, the power system architecture facilitated lower training times without compromising the algorithm's accuracy for each of the dataset. As we all know, in machine learning, for evaluating a model, we should look into the performance of the model in terms of both times and accuracy. We present the accuracy scores and training times across the 4 datasets for both the approaches mentioned before. Before we get any further, I'd like to give you a quick introduction on our runtime environments we used throughout the experiments. Except for CatBoost, all the algorithms were executed on the datasets on the Power System AC922 CPU. IBM's Power System AC922 delivers unprecedented performance for analytics, artificial intelligence, and modern high-performance computing. The Power AC922 is engineered to be the most powerful training platform available, providing the data and compute-intensive infrastructure needed to deliver faster time to insights. Data scientists get to use their favorite tools without sacrificing speed and performance, while IT leaders get proven infrastructure to accelerate time to value. This is IT infrastructure redesigned for enterprise AI. Now my colleague Shyam will describe the datasets we used, the 4 algorithms, and give you an overview of the hyperparameter optimization technique we used.
Let me start off by giving you the details of the datasets that we used for our experiments. All the datasets that we used are publicly available. We specifically chose a broad range of datasets to ensure that specific algorithms are tested for flexibility and adaptiveness to different data formats. Our first dataset is the numeric dataset, which is Pokemon numerical. It contained 800 numeric entries and 11 features, with the objective being to predict whether or not a Pokemon is legendary. Given the values of features such as HP, attack, defense, special attack, and special defense, etc. 30% of the data was used for testing. Next, the categorical dataset, which was Pokemon categorical. It had a similar objective as that of the numeric dataset, but had 6 categorical features and 800 categorical entries. 30% of the data was used for testing here as well. The image dataset that we chose was the well-known CIFAR-10 dataset, which consisted of 60,000 32 by 32 color images with 10 classes in 6,000 images per class. It includes 50,000 training images and 10,000 testing images. Our fourth and final dataset is the temporal dataset, in other words, the time series data. The dataset that we chose was the daily minimum temperatures at Melbourne. It had 3,650 entries comprising of 3 years worth of data. So essentially, we tried to test these GBDT frameworks on as many diverse datasets as possible. This should help expose the weaknesses and identify the strong points of each of these algorithms. Well, now it's time to talk about our competitors, the boosting algorithms themselves. As mentioned before, we compare some of the top gradient boosting frameworks. To reiterate, XGBoost, LightGBM, CatBoost, and SnapBoost. Let's examine some of the key features of these algorithms one by one. First, XGBoost. XGBoost is a machine learning algorithm based on decision trees that uses gradient boosting frameworks. It was developed as a research project at the University of Washington and has been credited with winning numerous Kaggle competitions. The two main standouts of XGBoost are system optimizations and algorithmic enhancements. As far as system optimizations are concerned, XGBoost supports parallelization, which is possible merely because of the highly interchangeable nature of the loops used for building the base learners. The outer loop enumerates the leaf nodes of the tree, and the second inner loop calculates the features. Tree pruning. XGBoost uses max depth parameter as specified instead of the criterion first, and it starts pruning the trees backwards. XGBoost also incorporates several hardware optimizations accomplished by cache awareness, buffering, and multi-threading. Coming to algorithmic enhancements, XGBoost supports regularization, sparsity awareness, weighted quantile sketch, and cross-validation. Our next algorithm is LightGBM. LightGBM stands for Light Gradient Boosting Machine, and it was developed by Microsoft Corporation in 2017. It is a robust, distributed, and high-performance gradient boosting framework that is used for classification, ranking, and many other such machine learning tasks. The word light owes to its surprisingly fast nature. The algorithm uses a novel technique of gradient-based one-side sampling, in that it keeps all the instances with large gradients and performs random sampling on instances with smaller gradients. LightGBM splits the tree leaf-wise, whereas other algorithms splits the tree depth-wise. Our next algorithm is CatBoost. CatBoost is a recent open-source machine learning algorithm from Yandex. It can be easily integrated with modern deep learning frameworks such as Google's TensorFlow or Apple's Core ML. It performs very well with diverse datasets, and it helps solve a wide range of problems that businesses face today, making it an ideal candidate for our analysis. CatBoost is also appreciated for its ability to outperform algorithms when it comes to handling categorical features. Previous algorithms tackled this issue of sparse features by exclusive feature bundling. CatBoost is also 13 to 16 times faster than predictions made by other libraries, according to the Yandex benchmark. The last algorithm that we examine is SnapBoost. SnapBoost is a boosting machine which is available under the SnapML library developed by IBM Research Zurich. SnapBoost performs a functional gradient descent to learn an ensemble of decision trees. The boosting machine does not take a heterogeneous ensemble of decision trees. Instead, it takes a probabilistic approach to select the maximum tree depth at each boosting iteration. SnapBoost can be used for a variety of classification and regression tasks. Coming to hyperparameter optimization. Hyperparameter optimization, or HPO, is a technique through which one can considerably improve the accuracies of the algorithms by carefully tuning the baseline model's hyperparameters. Apart from manual tuning, which is cumbersome, there exist several automatic hyperparameter optimization frameworks such as Grid Search CV or Randomized Search CV. We use the HyperOpt framework for our experiments. HyperOpt utilizes a tree of Parsons estimator, or a TPE approach, for selecting the optimal hyperparameter through a specified number of iterations. To give insights on the HPO process, in our analysis, we provide the necessary iteration graphs of HyperOpt and also provide a comparison of the accuracies obtained by the algorithms with and without using HPO. Now that we've established our experimental methodology and had a comprehensive overview of the algorithms and the datasets that we used for our analysis, Vinayak will now walk you through the results that we obtained from our experiments.
As mentioned previously, we trained XGBoost, LightGBM, and SnapBoost with the 4 datasets on the CPU on the IBM Power System AC922 server. With and without the usage of HyperOpt, the same was done with CatBoost on Google Colab CPU. We plot the accuracy achieved by the algorithm and the training time in seconds obtained in all the cases. HyperOpt adopts the tree of Parsons estimator for hyperparameter tuning. For the purpose of illustration of how HyperOpt works, we have provided the HyperOpt iteration graphs for several hyperparameters. These graphs will enable the reader to better understand the range of values through which HyperOpt iterated for each HP. It is also helpful in determining the optimal value of a HP for which the accuracy of the model was the highest. The chosen optimal HP value is highlighted with red color in the graphs. Interested viewers can feel free to check the graphs I demonstrate here on our GitHub repository, which will be provided at the end of our talk. Firstly, we examine the performance on the numeric dataset. Here is the accuracy plot for the algorithms on the numeric dataset without HPO. SnapBoost performed very well with 99% accuracy in predictions, followed by the CatBoost with 98%, and LightGBM with 95.83%, and XGBoost followed closely with 95.82%, which all are good performances without any optimizations. In the case with HPO, while CatBoost and SnapBoost had more or less the same accuracies here, LightGBM and XGBoost showed an improvement of 2 to 3%. Here are the HPO graphs. The x-axis contains the value of the hyperparameter, and the y-axis contains the accuracy obtained. As shown, the tuning process was carried out for several HPs for all 4 algorithms individually. The best suited for or optimal combination of HPs are auto-selected by HyperOpt, and we have highlighted them in red color. On the top left, the selected value of the hyperparameter is also printed for convenience. Now, for the training time plots, LightGBM is the fastest without HPO, and SnapBoost being the fastest in the latter. Next, we examine the performance on the categorical dataset. Here is the accuracy plot for the algorithms on the numeric dataset without HPO. On the categorical dataset, CatBoost outperformed the rest by achieving 99.5% accuracy. The second place is taken by SnapBoost with 98%, while XGBoost with 97.24%. That narrowly overtakes LightGBM with 96.68%, giving a tough competition. With HPO using HyperOpt, all the algorithms showed an improvement in performance. SnapBoost improved by 1%, while the others improved by 2%. Here are the HPO graphs. Now, for the training time plots, in both the cases, SnapBoost performs extremely well, especially when coupled with the PowerAI architecture. Now, for temporal data. Without HPO, on the temporal dataset, LightGBM beats the rest and achieves the highest accuracy of 54.45%, while CatBoost achieves a 54.12% score. XGBoost fails miserably. With HPO, SnapBoost showed the most promising improvement by 27% increase in accuracy, while all others showed an improvement of around 13 to 16% in the accuracy. Once again, here are the HPO graphs. Now, for the training time plots, with SnapBoost once again beating them all to the finish in both the cases. Finally, we examine the performance on the image dataset, observing the accuracy plots for both the cases we have. Without HPO, on the image dataset, CatBoost is the clear winner as it achieves an accuracy of 61%, while SnapBoost, not far behind, manages to achieve a 50% accuracy. LightGBM again fails here with a mere accuracy of 10%. With HPO using HyperOpt, XGBoost showed an improvement of 13% increase in the accuracy, while others showed only a marginal change. The HPO graphs are shown for reference again. And lastly, the training time plots. XGBoost and LightGBM steal the show this time, in the case of using HPO. But nevertheless, SnapBoost has a considerably good speed overall. So these were the results of our analysis. Now Anubhav will summarize the results we have seen and draw some inferences and insights from this experiment.
So are you guys excited to know who has won the war? Let me walk you through the inferences of the experiments being performed. All the algorithms were validated for being robust against overfitting, ability to handle categorical variables, and multimodal data while leaving a small memory footprint. Our research aids in improving the explainability of GBDTs across several use cases. On examining the performance of algorithms on 4 diverse datasets, we infer that the most consistent performance in terms of accuracy and training time was seen in SnapBoost and XGBoost across all the datasets. XGBoost was always second or third in terms of training time and put up a stiff competition with other algorithms in terms of accuracy. CatBoost worked very well for categorical data and outperformed the other algorithms in image as well, but was the slowest algorithm in 3 out of 4 cases. LightGBM is very fast in terms of training on all datasets excluding image data, but its training time prowess is marred by its inconsistency in accuracy. SnapBoost showed good performance on temporal and numeric dataset, and it is consistent in terms of accuracy. The huge highlight being that SnapBoost, when run on IBM Power Server System AC922 server with HPO, is the fastest algorithm in terms of training time, which is then followed by LightGBM. We have observed several improvements in accuracies of all the algorithms after using HyperOpt for hyperparameter optimization. It reduced overfitting in some of the cases, while in others, it helped in making better fits to the data. On behalf of the team, I would like to conclude this talk and also remind the viewers that this challenge of building a robust GBDT framework that excels in all scenarios still continues to be an open problem, despite extensive research in this domain. Also, we would hope that the research has substantially aided the future enhancement on ongoing work around the GBDTs. We would like to thank you all for lending your ears. Feel free to contact us for any queries regarding the talk. Speaker social media links and GitHub links for entire work is provided in the next slide. Kindly feel free to contact us for any queries or opportunities. Thank you.